In this chapter, we learn some of the really cool things that can happen involving excited states of molecules. So we're going to start out and just define some of the possible transitions that we can have involving excited electronic and vibrational states in some molecular system. So I've started off and I've drawn here a series of potential energy surfaces. And we'll start out here. This is the S0 or the ground state potential energy surface of some system. So we're looking here at energy, this potential energy surface traced across some internuclear coordinate r. And so if this were a simple internuclear coordinate, this would just be the distance between two atoms in a bond. And we know that this minimum represents the equilibrium bond distance, and this represents the electronic energy of the ground state as we stretch and compress that bond. And so that gives us then the vibrational states of the ground state. Now, when we introduce a photon, we can potentially excite from this ground state into some higher lying excited state. And so we'll take a look first at this S1. So this is a singlet excited state, getting the subscript 1 as opposed to 0 because it's an excited state. And we know from our discussion of electronic transitions before that the optically allowed transition is from the singlet state to the singlet state because we can't undergo a spin flip upon photoexcitation. We also know, given Frank-Condon factors, given the Frank-Condon effect, and which of course comes from our Born-Oppenheimer picture, that we're going to make a vertical transition, and so our absorption of light, we will excite like this. And so starting out in the ground vibrational state, in this ground electronic state, will be most likely to jump up to somewhere around there in our excited state S1. Now, immediately following that, we're now in an excited electronic state. So our electron is existing in this S1 state. What'll happen after that is this will start out in, say, some vibrational level of the excited electronic state, and that will decay down. And so this will fall down to subsequently lower and lower. These are a series of downward pointing arrows in case that's not clear on the camera. So we'll drop down these vibrational levels to the bottom level of our S1 excited electronic state. And so this we would call vibrational relaxation. And so when we make these downward transitions in our vibrational levels, this is typically happening in a non-radiative manner. In other words, this is not emitting infrared light, primarily because that process of emitting infrared light is very slow and unlikely to happen. In a condensed phase system, a molecule in a liquid state or a solid state, and really for any polyatomic molecule itself, even any gas phase atom that has, or any gas phase molecule that has more than about 10 atoms, these vibrational transitions will hop downwards without emitting any light. And where this energy will generally go to is, it doesn't just disappear, this goes to other vibrations of the molecule. And if this is a molecule in a liquid, this will be transferred to vibrational motions and rotations and other movement of the liquid. So this will basically be given off as heat and motion of the molecule and its surroundings. Now, once this molecule reaches the bottom, it could potentially hop back down. And this might be a radiative transition. if this is a radiative transition, this is actually emitting light. So be emitting probably visible wavelength light, following this de-excitation from our S1 excited state into our S0 ground state. And so some photon comes out. Now it is possible, right? I did say these vibrations lose energy to their surroundings by causing excitations of their surrounding. It is possible that this could decay in a non-radiative manner. I'm going to indicate this with a squiggly line like that. And in this case, it is possible that this large amount of energy could go toward excitation of some other either vibrations of this molecule or other excitations, either electronic or vibrational, of other molecules in its sort of nearby vicinity. And so these two decay processes actually get two separate names. This is a radiative transition, and that radiative transition from an excited state to a ground state of the same spin is called fluorescence. And so lots of things fluoresce. This white paper is actually enhanced to be especially white. All white paper that you interact with is enhanced to be white. This white paper actually absorbs in the ultraviolet and emits a lower energy photon via this fluorescence process to actually enhance the whiteness of this paper. So this white paper actually looks more white than the room light. Now the other process is internal conversion. That's this squiggly line here. This is where light hits our molecule, and that excitation goes to excitation of another molecule, either an electronic excitation or a vibrational excitation. I've indicated this with a squiggly line, and that's fairly typical. Your textbook uses a dotted line, and that's also fine. Now, another possibility for decay is we do have this other state up here, this T1 triplet excited state that I haven't really talked about in this system. It is possible to end up in this triplet state. Now, we can't make a direct transition from our singlet ground state to our triplet excited state because this is spin forbidden. We can't have an excitation in which the electron flips sign, really because light can't induce that kind of transition. But we can have an excitation where we go up to this singlet state and we decay down to the bottom. And then with a little bit of extra energy, we can kind of come up here. And so this will require a little bit of heat in the system. We'll come up here and make it over that barrier and undergo a spin flip. This is a fairly slow process. By slow, I mean picoseconds. But we can potentially come over here and end up actually in our triplet excited state. This process of going from a singlet to a triplet state is called intersystem crossing. And so we can end up over here, and again, we will undergo a series of vibrational decays and end up at the bottom of our triplet potential energy surface. And now we have this situation where we're kind of stuck because a triplet state we cannot use a photon to excite to that triplet state. And for the equivalent reason, we also are spin forbidden from making a direct transition down to our S0 ground state. So this process will be slow. It is possible, just very unlikely, and therefore will take a long time, to undergo a de-excitation from this triplet state to this ground singlet state. So this process, we might be stuck up here for an extremely long time, perhaps even hundreds of nanoseconds, where we're stuck up here in this triplet state before we can decay down back to our singlet ground state. That process is known as phosphorescence. And so phosphorescence is, again, something that we actually encounter quite often in everyday life. I'll make another comment here specifically about the absorption and fluorescence. This vertical line again here is the fluorescence. So what do the spectra of absorption and fluorescence look like? We talked about before, we will make some excitation up here to an excited, this is our S0 and our S1. We're going to make a transition to our excited electronic state and one of these vibrational energy levels. And we know from the Frank-Condon principle that the vibrational energy level that we will be most likely to end up in is the one where the classical turning point of the excited state lines up with the minimum of the ground state. But of course, there is some likelihood that we'll be able to end up in any of these states. And so that will look like, if we were to plot out intense, I guess this would be absorption versus energy, right? We will be able to see transitions to a large number of these vibrational states, and these might show up as individual wiggles in our spectrum. And this peak in the absorption spectrum represents our Frank-Condon maximum. So we're most likely to end up the way I drew it. We'll end up most likely in this vibrational state in the excited electronic energy level. Now, what about fluorescence? Again, fluorescence, we're going to make a series of transitions down to, oops, I've gone past the bottom, go down to this bottom state here. And once we're in this bottom state, we're going to make a transition back down. And again, we're going to follow Frank-Condon rules. And so we will end up something like this. We'll be able to make transitions to any one of these different vibrational states. We will have a state that we're most likely to make transitions to, and that will be our Frank-Condon maximum for fluorescence. And something interesting that happens in the spectra is if the overall curvature of our ground state is similar to the curvature of our excited state, which seems fairly likely, then in that case, our vibrational energy level spacing in the ground state will be similar to the vibrational energy spacing in our excited state. And our intensity of our fluorescence spectra will essentially mirror, this is not my best drawing here. This will mirror the shape that we saw in the absorption spectra. So we're going to see this same overall shape again in the fluorescence spectra that we saw in the absorption spectra. So this gives you just a little bit of an idea of the types of energy levels and transitions we can consider and how we can have various different excitation and decay